So, first of all, has anyone actually heard of Ceph at all? Oh, wow, okay, a fair bit. How about used it? Not bad, not bad. And configured it yourself, bootstrapped it off the ground, run through the documentation? How about done that without Ceph deploy? Okay, we got 1, 2. So, Ceph, let's see if I can figure out how to work this, is a storage cluster. It is in some ways to storage as CoreOS is to compute clusters. At its core, Ceph is an object store, but it's a key-value storage database for arbitrary chunks of binary data. It has a number of components which allow it to work to wrap all your needs into one unified cluster. This is Rados. It's the heart of Ceph. It provides an infrastructure for creating large-scale distributed storage clusters with no single points of failure. Various levels of redundancy control and awareness, various storage organization mechanisms, classification abilities, and distribution means, and fully and proactively automated data redistribution based on changes to the architecture and involvement in the network. Basically, it wants to do everything storage for you. The object store itself is great, but most people want a little more than just library access layer to access their storage. To facilitate this, Ceph adds a number of component layers on top of Rados. First, we'll start with Rados GW, or Rados Gateway. This is a REST-based interface that allows manipulation of stored chunks of data, with some administrative glue added on, like buckets and authentication. Basically, this is your own S3. In fact, it's API compatible with Amazon S3, as well as OpenStack Swift. Next, the RBD, or the Rados block device. This is much like a network block device, except it attaches directly to Ceph. It's a way of clumping a whole bunch of data stored objects together as a block device that a client operating system or container can use directly and natively as a file system. Conveniently, CoreOS also has everything you need to make this work, with the exception of little glue wrappers that we've put together as part of the Ceph container project. Lastly, there is Ceph FS, the clustered file system. Much like Gluster or other clustered file systems, it's a multi-access, multi-read, multi-write system that's POSIX-oriented, not really POSIX-compliant, but POSIX-oriented file system, which, having kernel support, allows you to use your Ceph cluster directly and natively as a file system. Conveniently, again, CoreOS includes support in the kernel for Ceph FS. As a matter of fact, you don't even need any glue layers for this. To use it in your CoreOS on any or all of your CoreOS nodes, all you need to do is mount the Ceph FS file system to a mount point on the host. You do need to be able to authenticate, since most Ceph clusters should have some sort of authentication control. But at the basic level, you just need your access key and the mount command, which comes with CoreOS. Now, I'm not a Ceph developer. I don't work for Red Hat. All I did is write a set of containers to work with running Ceph on CoreOS. As with most such things, I designed it to scratch an itch. Two, in fact. I wanted to be able to run VMs on top of KVM, on top of Docker, on top of CoreOS. Yes, that's ridiculous. But I also wanted to be able to store, to use databases on CoreOS. And of course, one of the main problems that everybody hears about is how do you store persistent data on Docker and CoreOS. So because I use these common components, because I use these components on Fleet myself, each of these components in the GitHub repo includes sample Fleet files so you can make minor modifications and use in your own CoreOS clusters. At any rate, after I made these initially, rough as they were and intended just for my own consumption, I was approached by Sebastian Hahn, now of Red Hat, to migrate my containers over to the official Ceph namespace on both Docker and GitHub. And anyone, by the way, who has played with Ceph should know Sebastian. He has an excellent blog on Ceph and a number of other things, sebastian-han.fr. But I'll reference that again at the end. Since then, with the additional community support, we've grown quite a bit, and the Dockerized Ceph containers are quite usable and much more flexible than the initial implementations. Now, for those few that have bootstrapped a Ceph cluster yourselves, you know that while the documentation is fairly extensive, although it does have 2 layers of documentation, so you have to make sure you know which layer you're operating on, it's not particularly easy to get a Ceph cluster up and running, particularly if you can't use Ceph deploy, which, of course, CoreOS and Docker, there's no support for Ceph deploy in there. However, we have set up, again with community support, a number of things to make getting Ceph off the ground in CoreOS very easy. Our cephmon container includes everything you need to get Ceph off the ground. It automatically generates keys. It automatically generates the mons, the initial mon that you're running, and most of the stuff is done for you. Additionally, we now have a complete bootstrap, which includes a container that starts up everything, generates a config file, stores it in etcd, and starts up an OSD and a mon automatically, so you have a fully functional Ceph container in a cluster, or cluster in a container. Eventually, and hopefully in the near term, we want to integrate this with etcd fully, along with confd, so that you'll be able to bootstrap an entire Ceph cluster, multi-node Ceph cluster, purely declaratively through etcd. It's not there yet, but at least for now, it runs quite well with environment variable definitions extracted from fleet unit files. So, what can we do with it? What are some of the compelling reasons to integrate Ceph into your cluster? So let's start with a small but very common problem, machine-agnostic persistent storage. We want to be able to have state for our containers that can migrate around the cluster wherever we need it. Say, for instance, for the backing store of a database. So how many times at this conference have you heard the question of how to manage this persistent data across the cluster? Ceph is one answer to this question. We've made a number of very convenient Golang-based mount and unmount service, a very convenient mount, unmount service, which runs as a sidekick service that, again, you can run from Fleet, which mounts an RBD volume into Docker so that you can use volumes from or a bind mount to have as a sidekick process your data stored in Ceph. There's no translation, there's no import, there's no export. It's just there directly accessed through an RBD volume. So you don't have any additional latency involved in the transfer of that file. If it's a gigabyte database or larger, you don't have to transfer that entire database to that node. It's immediately available on an ad hoc basis as a block device. So I realized just before this talk that I don't have an example of this in the repo, so I will be adding that to the repo after this talk. I should also add here that it's probably the wrong way to architect your system to use Ceph in this way and to have a sidekick process that manages your stored data. Much better to actually architect your system in a more container space idealized way. If, on the other hand, you're dealing with an archaic service that expects it to be in the file system and you have no other way to manipulate it, this is a way to work around that. So it's a powerful feature, but really, don't abuse it. Write your apps correctly if you can. So let's look at a slightly larger problem. Abstracting storage. Say you have a magnificent private storage network, a SAN, built like a brick outhouse, or perhaps a really solid and rugged Nexenta system, or maybe one of the super expensive, fancy InfiniBand networks that you can get gigabits of IOPS in every part of it. It operates beautifully and has never failed, never had any problems, and great everything. But suddenly you have this need to grow. You have a new client who has a much larger system than what you can currently store. Now, of course, you can extend your storage, but that might take weeks, months even. You need a way that you can extend your storage now to be able to handle the new growth. And yes, you may not have it quite as good as your internal storage, but you'll be able to at least tolerate it. And more importantly, you'll be able to keep the data that you need local while still maintaining separate backup for replication and keep it classed. So add Ceph into this mix, abstracting away the local storage mechanisms, and you can immediately leverage the cloud-based storage or even cheap, inexpensive disks and a whole bunch of workstations that you just happen to have lying around the office and that work, and throw them into the Ceph cluster. None of your API access changes. None of your methods of accessing the storage change. And immediately when you add those devices, Ceph automatically starts migrating the data and balancing it out to properly maintain the levels of replication, all based on a consistent class that you've predefined for your storage. So again, you gain rapid scale-out, easy addition and subtraction of components. This is important. When you migrate some elements to the cloud, you would then later have your local storage that's screaming fast and ultra-reliable and everything. You can just as easily remove the cloud components from the Ceph network, all with no downtime, all with no interruption of service, and no reorienting of your application space at all. So fully automatic redistribution data and flexible storage classes, all of that. Really great stuff. So how about if you're already running on the cloud? You already know this rapid scale-up. That's not a big deal. It's handled by Amazon, GCE, whatever. So AWS has some great storage features, and most of the cloud providers do. So what does Ceph actually bring to the table? What if you had a need to run across a whole bunch of different cloud providers? What if you needed to access competitive pricing? Or perhaps you have a customer who has specific needs of where his particular data needs to be stored. For instance, government entities which need to have it in this particular location and not in this one. So Ceph handles all of this for you. In fact, if you were to use a Ceph overlay on top of your existing cloud storage, you'd be able to manage exactly those kind of controls and processes on any cloud platform, internal, external, add and remove as needed on the system as a whole. So you can leverage multiple providers on the same cluster, use a common architecture for all your services, and leverage location-based distribution rules to make sure that your data is stored precisely where it needs to be for each customer, for each application, for each use. So all of that sounds pretty great. But there are some rough edges. We've worked around most of these, but there are still some big ones you need to know about before you run Ceph on CoreOS and Docker. So NAT, a big one. Ceph doesn't tolerate NAT at all. Just forget it. Don't try it. And this is true for pretty much any of its components. Mons, OSDs, whatever, don't do NAT. Not only that, but it doesn't tolerate IP changes. So while you may be able to run on an overlay, if you are not maintaining static assignments of those IPs, you're going to mess up your entire Ceph cluster in a heartbeat. So this means almost certainly that you want to run your Ceph components with net equals host. Now again, some overlays, particularly like as from the last talk, Calico, sounds really great in that you can associate in particular IPs with containers. And while I haven't actually tried it, I'm definitely going to try that, having just learned about it, thankfully. Port storm's another problem. So Ceph components can be cohabited on the same machine. But when you do so, they expect the PID namespace to be the same. Otherwise, it very rapidly runs out of ports. And when I say rapidly, I mean within 5 seconds, your 65,000 ports on your machine are completely exhausted. Your system load goes to infinity, and you have 0 throughput on your I/O. It's very bad. So if you ever have the need to, or ever plan to run multiple Ceph components, this includes multiple OSDs on the same machine, make sure you execute with PID equals host, or use a common namespace for your Ceph components for your PIDs. RBD access. So there are some kernel-level accesses that Docker doesn't handle without privileged mode. This is primarily in the RBD space, but it also impacts BTRFS-backed OSDs when you use BTRFS native journals. So in either of those cases, you'll need to run the affected containers with privileged, unfortunately, at this point. So finally, the daemon indexing. It's hardware specific, or more specifically, the mononode OSD have IP address and storage associations that are not movable, migratable around the data. Now, this is bad, but also keep in mind you're building this storage cluster in order to allow your applications to then be migrable. So it is something of a sacrifice, but particularly if you bind it with Fleet's machine ID and use some instance IDs to correlate it with the machine IDs, you can pretty well run Ceph components on Fleet without a problem. You just have to be sure you know what you're doing and maintain that hardware binding. So Ceph generally gives you a lot of flexibility. It's not yet a turnkey solution, but much like CoreOS, it's a set of tools that allows you to build a massively scalable, highly flexible storage system. So we have a few things coming to our containers. In addition to the conf-d-based automation, which is really what I'm looking forward to, we've also got a Kubernetes Bootstrap that we're working on, and much more integrated support for Red Hat-based systems. Ceph now is owned by Red Hat, so that's to be expected, one hopes. So more than anything, though, we need people to use the containers, find bugs, come up with features, whatever, generally be involved. We've had a great support so far. Lots of people have helped with this project, in addition to the Ceph people themselves, of course. So since moving to the official Ceph namespace, we've gotten a ton more ideas, much better implementations and everything than anything I bothered to cobble together myself. Ceph isn't for everybody, but it's a great open source reimagining of what cluster storage should be. So, any questions? All right. Or by microphone.
If you're running a database like, let's say, MySQL on top of one of these distributed store like Ceph, how do the native clustering features of your database application come into play? Do you stop using them and just use the distributed store? Or?
No, in all cases, you definitely want to use your clustering capabilities of the database itself. Really, what this replication is key to availability, if nothing else. What this allows you to do instead is be able to machine abstract those database instances. So at this point, you can just say, run MySQL A, and it doesn't matter what node that's stored on. You don't have to worry about the underlying storage, the disks that are available on that machine. So you no longer have to tie that instance of MySQL to that machine. Likewise, there are some other solutions where you spin up a new MySQL instance and you pull down the existing data, which is great and works well with the clustering, but it also has latency involved. So instead, what you're doing is really migrating around the system and just pointing to the data. And that's what our RBD mount container allows you to do.
Just a couple of simple questions. One was, you mentioned that they have to be privileged, the containers. I'm guessing those are just the Ceph containers, or the actual containers that mount?
No, and even then, just a few cases where you have to run in privileged mode. One being the RBD. Basically, RBD is a kernel call. You need access to kernel level. You need the device tree. You need the proc tree. You need a few other things. And then, very specifically, you can run most OSDs without privileged. And when I say OSDs, these are the daemons that run with storage to actually manage access to the real storage. So they're basically the proxies for the disks. But you can run most OSDs fine. However, if you run a BTRFS formatted OSD and leverage journaling inline on that same storage disk, on that same BTRFS file system, you need kernel access support. Those are the only two cases I can think of at the moment which actually require privileges, and those are only applied to the Ceph containers themselves that are affected.
Just one more, a little more important question. Have you gotten it to run on Raspberry Pi?
Have I tried? No. Anything else?
Do you have a production implementation of this running? Has it been stable and scalable? And, or is it just a sort of adventure in how we do it?
So the question is, do I have a production implementation of this? Has it been stable? Has it been well run? Yes, I have it in production. Is this wise? I'm not so sure. Particularly when you're testing, for instance, the upgrade between Firefly and Giant on your production cluster, things don't always work as well as they might should. At any rate, no, actually, I've not had any problems, except in that particular case, I had a rather massive disaster taking down my Ceph cluster for a few days because that particular production cluster had all motherboards of the same type that I just happened to, a few days before, upgrade the BIOSes on, and the combination of the upgrade of the BIOS and the Firefly enabled, I can't remember exactly what it was, but something on the disks which made them silently corrupt themselves in the background, which was really nasty. So archives, external archives, still a really good idea. But yes, I do use it in production. Yes?
So, where are the Ceph containers storing their data? How does the volume thing work?
So the question is, where does Ceph actually store the data? Let me ask this, and corollary to that, where's the volume information? So Ceph has a number of different daemons associated with its core processes. OSDs, object storage daemons, are, like I mentioned a little bit before, are the daemons which translate and proxy requests from the cluster to specific disks or sets of disks. So for any discrete storage entity, usually these are disks, but sometimes it can be RAID arrays, they can be network-attached storage. At any rate, whatever you're defining in your cluster as a single disk storage entity runs an OSD. And the actual data stored underneath uses a normal file system. It's just a particular Ceph set of directories and orders on top of that, which creates the objects that are referenced. And you have a database that Ceph also maintains, which makes the mappings to those databases. So all of that is abstracted away when you're running Docker. The only thing you see, for instance, if you're using an RBD volume for Docker, is a block device. To the system, to the operating system, to the container, it looks like any other block device. Behind the scenes, the kernel driver will actually look up to the monitor, to a Ceph mon, get the actual redirects, and find where that data is and pull it in, all behind the scenes. And interestingly enough, also obeys various caching and write-through requirements. For instance, for RBD volumes, in particular classification groups, placement groups, You might want to have performance overall, so you might set that particularly to only worry about when it's caught onto the journal and received in order to confirm a write. Other times, you might actually have mission-critical data which must be replicated before you consider that complete. Ceph handles all of that in the background. It's all declarative in the configuration, and you set it up with the groups.